All right, great. Thanks for the introduction. Okay, so yesterday I talked about neutrino flux, which is something that I pay a lot of attention to as well. But today and tomorrow's lecture will be focused on neutrino scattering. And so today's lecture will be, excuse me, will be the why and how of neutrino scattering. Okay, so first of all, again, I just want to apologize that I cannot be there in person to meet and talk with you, with everyone there. But since it is a school, throughout my slides, I have some questions that I would like you to answer afterward. And I encourage everyone to please send me at least one follow-up question after each lecture. I didn't receive any questions yesterday, so I don't know if you're being shy or maybe the school is just too intense, but I do want to make myself available to you. So I encourage everyone to send me questions. And then I will post the answers in the Slack channel that the school has set up. So yeah, you can send me questions either via email or Slack. Okay, so what I'll be talking about today a bit is, so first of all, why do we care about neutrino scattering? Why is it so important? Then I'll talk a little bit about the role of neutrino event generators. Then I'll go into really what goes into a cross-section measurement. What do we have to do to extract a cross-section from our data? And then I'll as I talk about that, I'll also be discussing how to avoid model dependency in cross-section measurements and model bias. Okay, so before I get into explaining the practical reasons why we care about cross-sections, let me just say, or at least state that cross-sections in and of themselves are really interesting. Neutrinos are a unique probe of the nucleus, being a massive but nearly massless particle, and only interacting through the weak current. It offers some unique capabilities that other particles don't. And there's some very interesting physics there that we, in principle, can probe with neutrinos. Now, on the more practical side, I spend most of my time working on long baseline oscillation experiments. And so for me, cross sections are also a very practical thing to be thinking about, because they play a really critical role in how we extract and how well we can extract the oscillation parameters from our data. So as you recall, we see neutrinos because they scatter off of nuclei, producing charged particles that deposit energy in our detectors. And a critical part of the number of events that we record in our detectors is just the cross-section itself, right? And the cross-section is the probability that a neutrino scatters in our detector. Okay, now lots of different things can happen when a neutrino scatters, right? You learned about this last week. But there are, if you look at the equation, right, we have the flux times the cross-section times an efficiency, right? And so there's the cross-section term, which I showed here, right? So we need to know that number, or we would like to know it as well as possible. And then when it comes to the efficiency, what this means is, we look at our data, and as you heard from Adam yesterday, we have to take our data and then we have to do some sort of reconstruction, right? We have to, it's like taking our detectors are like really fancy cameras. And so we take a picture of stuff that's coming out of a nucleus, right? All of these particles. And then we have to infer what actually happened. In other words, we have to infer what is the energy of the neutrino, what type of neutrino is it, that kind of thing. Now, when we take a picture and we try to figure out what's going on, we have to look at the event and make some decisions. So if we want to get a good measurement of our neutrino energy, then we need to measure the energy of all the particles. And in the absence of a magnetic field, that means we want to have the muon stop. That way we know when it stops, it has zero kinetic energy, but we know where it started, so we can backtrack and we can get the energy of the muon. But if the muon exits out the side of the detector or exits out the back, we won't be able to use that event. And so what we do is we reject that event. We know that we've rejected it. We keep track of that, but we need to correct for that, right? And that's called the geometric acceptance correction. And then, but there could be other more complicated things where maybe the muon is buried inside of a very busy hadronic shower, so much that we don't actually see the muon itself, right? It's covered by all sorts of other particles that are coming out of the nucleus. So we have to select our signal interactions, but our selection is imperfect. The rate at which we select our signal events is our efficiency. And the efficiency basically depends on the differential cross-section for producing all the final state particles for all interactions at a given energy, right? So the efficiency itself depends on the differential cross-sections. Now, the other thing is that we're trying to measure oscillations, right? But oscillations occur for, what we like to call true neutrino energy, right? The neutrino has a real energy, right? And we have to infer that energy. We have to reconstruct that energy. And so that's our reconstructed energy. And so what we have to do is we have to look at our picture, and we basically have to account for all of the things that we don't see, right? So there are particles that we don't see, in particular neutrons, but they could also be very low energy particles, so low that like basically we can't even like easily recognize them with our pattern recognition software. And so we don't know the energy of the neutrino coming in, but we have to reconstruct it, and we do that using the measurements of the final state particles we see, and we create something called the smearing matrix, right? That smearing matrix takes the true energy, and it takes into account the resolution of our detector, and it also accounts for unobserved particles. And therein lies the model dependence, right? The dependence on the cross sections themselves. How often does a neutron come out of the nucleus? Or how often does a low energy particle come out? We have to have models for that, and those models are basically our differential cross sections, right? So the smearing that we apply in our experiment depends very much on how well we model our cross sections. Okay, and then and so you can have, for example, these missing particles, but you could also make a mistake, right? You could have a charged pion in the final state, but then get that confused by with a pion in the final state and confuse that with the charged lepton, meaning the muon, right? So pions and muons have nearly the same mass, and so they can look very similar in a detector. And so if it turns out that a muon was given low energy, it's not going to travel very far, but maybe a pion was created with more energy and it will travel further. And so now you've got the wrong particle with the wrong energy. And so this can happen, and then you end up getting the wrong neutrino energy as a result. Right? So this is again something else that depends on the differential rate, the probability of this happening is something that we have to worry about. So a question for you to ponder is, what else could go wrong with our event selection, right? So I gave you some ideas, but there are plenty of other things that can go wrong, and I'd like to hear your ideas on that. Okay, now we rely on, so we have all of these effects, right? We have the smearing, we have the cross-section itself, we have the efficiency corrections, which it can depend implicitly or explicitly on the cross section. And so we rely on models to determine all of these corrections, right? And these models are implemented in something called neutrino event generators. I believe it looks like you all had some tutorials on, I think it was Genie. And so we rely on generators to simulate neutrino interactions in the kinematics of all of the final state particles. Now, for the GeV neutrino energy scale experiments that we do mostly at Fermilab, but also at JPark, there are 5 generators on the market that cover the physics that we need, or at least they try to cover the physics we need. So there's Genie, which is a generator that is used by all of the Fermilab experiments. Then there is Newt, which actually that logo is not their logo. They don't, I think, officially have a logo. So I just someone else actually came up with this idea of putting a Newt there. But anyway, the Newt generator is used by the Japanese experiments, T to K, Super K, and Hyper K. And then there's a new one on the market. It's very, very new, coming out of Fermilab, and this is a theory-driven event generator. It has been derived. One of the use cases for it is that it actually makes it very, very easy to put models for beyond the standard model physics in and generate events in Achilles. So far, Achilles has only able to predict the interactions in the quasi-elastic regime, but they're making very rapid progress, and pretty soon we expect that they'll have predictions for resonant and DIS and SIS. Then there's Jibu, which is another theory-driven event generator. And this is actually a very generic event generator. It's not just for neutrinos. This was originally developed for electron and hadron scattering, but they also added in neutrino. And it has one of the most sophisticated, most theory-driven final state interaction models out there. Of all of the 5, this is the final state model is really very theory-driven. Whereas everyone else basically uses something called something like a cascade model, where the final state smearing is kind of simplified at some level. And then finally, there's Neuro, which is also theory-driven, and it has many model options. Neuro is really nice because it's typically a very early adopter of new theory developments. And so it's nice to have Neuro when you want to compare something maybe a little bit hot off the presses or some other theory. And so, yeah. Okay. Now, the current neutrino experiments for the oscillation experiments, at least, cover nearly 2 orders of magnitude of neutrino energy. All the way down to a few hundred MeV up to several tens of MeV, or tens of GeV. So that's shown on the left here, the fluxes. But the life is made a bit interesting here, because if you look across this whole span of energies, you see that there are many different types of interactions that can occur, right? You have the quasi-elastic, you have the resonant, the DIS, and these all occur within the few GeV range, and they kind of start turning on, right? The DIS starts turning on around a few GeV. The resonant is kind of peaked around roughly 2 GeV. Quasi-elastic turns on at very low energies and peaks around a few hundred MeV. And so these are, so the event generators have to implement all of the models for all of these types of interactions. And so they have to cover a large range of different models. Now, as you've already learned, interactions at the GeV scale are often characterized by their scattering off of bound nucleons and their final state. And so in the quasi-elastic regime, you have a neutrino coming in, hitting a nucleon, and it basically knocks out another nucleon and produces the partner lepton with it, right? So if it's a neutrino and it hits a neutron, then you end up with a negative muon and a proton. Then as you go up to higher energies, now you're probing a little deeper into the nucleus, and you are now interacting with quarks, and here you're creating a resonant particle, a delta resonance, and the delta is created inside the nucleus and then decays, and when it decays, it produces a pion and a nucleon, and of course, if it's a charge current interaction, then you end up with a muon or an electron in the final state. Then as you go to even higher energy now, you're basically blowing apart the entire nucleus, right? So you go in and you knock out nucleons, you can create several pions, etc. So those are the kind of the three regimes that we often talk about. But all of this happens in a nuclear environment, and that impacts both the initial state and the particles we observe in the final state. So if you look up here, inside of heavier nuclei, you end up with correlated pairs of nucleons. So perhaps a neutron and a proton pair that are correlated to each other. And when the neutrino comes in, it no longer sees a single nucleon, it sees a pair of nucleons. And now you have a three-body interaction, right, instead of a two-body interaction. And so this general process is called two-particle, two-hole, where you come in and you're basically knocking out two nucleons from the nucleus. And typically, actually, one of these tends to be pretty low energy. But then also, there are other things that you have to worry about. So the nucleus, of course, all of the nucleons are bound, but they're not at rest, right? They're moving around, right? So the fuzziness of this picture here is on purpose. It's supposed to look like things are in motion, and we have to model that. We have to model the initial state. What is the momentum distribution of all of these nucleons, et cetera? What is their binding energy, that kind of thing. And then there's intranuclear scattering and absorption have to be modeled, right? So once you have the interaction inside the nucleus off of, say, a quark, and you produce a pion, well, that pion then has to, if it's inside the nucleus, it has to get out of the nucleus for us to see it, right? And so sometimes it comes straight out and it doesn't interact, but other times it will interact on its way. And things can happen, right? If you start with a charged pion, maybe that charged pion undergoes charge exchange, and you end up with a pi zero in the final state instead of a charged pion, or that's over here, or maybe it's just simply absorbed. It doesn't have enough energy to get out, and it's just absorbed back into the nucleus. Or maybe the pion comes out and has enough energy that it produces even more pions on its way out, right? Pion production. So all of these things can happen, and these are all of the things that we have to model. And then a question for you is, what else has to be modeled? What else is there that we have to get right? Okay, so if we look at just some of the generators, so this table is a little bit outdated, but in general, it's still pretty valid. So here are 4 of the event generators, and as you can see, for their initial state here, they all use the LFG, the Fermi gas model for the initial state, and then some of them have the same underlying model for the quasi-elastic interactions. This is a model that came out of the so-called Valencia model by Nieves et al. Or it could be the Llewellyn-Smith plus some RPA corrections. That's a slightly older implementation of the quasi-elastic scattering. And then for 2P2H, you could have you could have different models. It turns out that in this case, they all have the same underlying model and principle. And then for resonance, there's Berger-Segal and others. Neuro has its own implementation for resonance. And then DIS, they almost all rely on Pythia, which is something that's used by collider experiments. It's very well tuned. It uses parton distribution functions that have been measured around the world. And then for the final state interactions, they all have slightly different approaches for doing this. Now, for the quasi-elastic 2P2H resonate in DIS, the Jubu model basically is kind of its own model here that is derived from first principles. It still uses a lot of the same pieces as a lot of these, but it's all kind of one cohesive, coherent model that covers this entire range. Whereas these are individual models that all have to be kind of stitched together. So the generators, as you can see from the table, they all use very similar and sometimes often the exact same model for exclusive differential cross sections. But as it turns out, it's different code, and the way that these models are implemented, they can be, and we have found them sometimes to be a little bit different, right? Even though it's supposed to be the same model, they don't always give exactly the same answer. And that's just because as you're coding things up, sometimes you have to take certain shortcuts to keep the computation down to a reasonable time, et cetera. Or just the way that one goes about calculating these cross sections. There are different algorithms for doing that, and they perform differently. So those can be different. And then on top of that, you have all of these individual models, but this is a quantum mechanical process, right? These things all happen, in a quantum mechanical probabilistic way. And so, like adding them together, you have to do that in a way where you account for interference terms and everything else. And so the total cross section at a given energy is basically the quantum mechanical sum of all of these processes, right? All of these cross sections. And as you can see in this plot down to the bottom here, as a function of W, which is the hadronic mass of the system, the invariant mass for the hadronic system in the final state. That as a function of W, you can see that there's pretty reasonable agreement up, in the quasi-elastic region, but then the models start to disagree very, very differently. And in fact, how they are kind of glued together, the quasi-elastic, 2P2H, the resonant, DIS, how these are glued together, you can see that sometimes there are just sharp changes, like here for Genie, right? It's just suddenly at was at 1.7 or something, 1.8 GeV, boom, it just suddenly drops down and follows this path, right? So there are, decisions that the generators have to make for a variety of reasons. Sometimes it's physics, sometimes it's just computational, but stitching all of this together is a very difficult process because honestly, we just don't know what the right answer is because we have limited data. So if you now compare just the inclusive cross section, this is an example for what we would expect to see in the NOVA detectors. You can see from three of these different generators that above about 700 MeV, they suddenly give very, very different predictions, right? The cross section is very different. And this is a result of the implementation and the stitching differences between these generators. It results in this spread. And so we want to make measurements, more measurements for cross sections so that we can improve our understanding of not just the individual processes, the quasi-elastic, 2P2H, resonant, etc. But then how to piece it all together, right? And so that's where measurements are really critical. So as we move to an era of precision neutrino oscillation measurements, the uncertainties on our models become a leading systematic uncertainty. So there's a global effort underway to measure neutrino nucleus cross-sections in order to improve these models and reduce the uncertainty. Okay, that's nice, but now how do we go about even making a cross-section measurement? So that's what I'm going to spend the rest of today is explaining to you how we actually go about it, so that when we look at some of the results, we have a better feel, a better understanding of what went into these. Okay, so first of all, I've already said, a cross-section is a probability of an interaction occurring. And obviously, the bigger the target, the more likely the interaction will occur, right? If you're shooting a bullet at a target, it's a lot easier to hit a bigger target than a smaller target, right? So the probability is higher if the target is bigger. And so the cross section is effectively a measure of the cross sectional size of for when an interaction will occur. And so the cross section is actually given in units of area, and you can think about it instead of the bullet hitting a target, but now a hard sphere where you scatter off of a hard sphere, right? And so when you do that and you measure the probability of hitting this, basically you're measuring the cross sectional area of the sphere. Now, elastic scattering is when, of course, there's no energy loss, right? And so elastic scattering occurs when we scatter off of a field, right? So this is a measure of the strength of a field. And then inelastic scattering is a measure of the internal structure of the target, right? Inelastic scattering is where the energy of your particle is lost. And it goes into something else. And in this case, we are knocking out a nucleon from the nucleus, right, and producing another particle here, or another nucleus here, all right. And so you can see where the elastic scattering cross section for a carbon nucleus kind of intersects with the inelastic scattering. As a function of the energy of the incoming, in this case is the incoming electron. And so for the inelastic scattering, you're just kind of like bending around the field, but for the inelastic, for the elastic scattering, you're kind of bending around the nucleus, but for the inelastic, you're kind of going into the nucleus and kind of blowing it up a little bit, all right? And and you can see the difference here that for a proton, which is a single nucleon, and a carbon has 12 nucleons, right? That the inelastic cross section is much higher than the elastic scattering, right? So, okay. Now, for a single target, that is like, for example, for a nucleon, the cross-section is simply the number of interactions that you count divided by the number of particles per unit area that you throw at it, okay? And so it's quite simple, right? This is pretty basic physics, right? Undergraduate physics. Now, that's for a single nucleon, but for a real target made of many nuclei, you then have to account for the fact that there are many more targets here. And meaning they're all of the nucleus inside the nucleus. Okay, now in a real experiment, right, if we want to measure a cross section, we have to select what we think are our signal interactions from our data. Now, this selection is an imperfect process, and so we have to make some corrections. Now, here I've added two new terms to the equation for the cross-section. I've added a P and an epsilon. So the P is the purity of the selection, and what you can think of that as a background subtraction. But what it is of the interactions that occur that are that you've selected when looking at your data, what fraction of them are true interactions that occurred, right? Of the ones you selected, right? And then there's the epsilon, which is the efficiency of the selection, and the efficiency is for basically it says what fraction, the efficiency is what fraction of interactions do you select that are like your signal selection, or that are your signal, all right? So when a true signal interaction occurs, what's the probability that you are selecting it, okay? Now, we often rely on our simulations to determine the efficiency and the purity, but we have to remember that simulation is always wrong, okay? This is something that I'm not sure that grad students hear enough, but if there's one thing that I really want you to take away from my lectures is that simulation is always wrong. And really the important question is just how wrong is it? We need to quantify our uncertainty on just how wrong our simulations are. Now the simulation is wrong for a variety of reasons. The models are imperfect, or maybe we make some choices in what we simulate to save some CPU time or something else, so that we aren't doing an infinite number of calculating small effects, right? So, but those small effects can add up after a while, right? So they can end up being, end up resulting in the simulation not being perfect. And so, so it's wrong. We have to understand how wrong it is, but we also have to develop a measurement that is minimally sensitive to the biases in the simulation itself. All right, now, so that's for so I showed you the equation for a total cross section, right? Now, those are nice. Total cross sections are nice to have, but what we really want and what we really need in order to improve our neutrino scattering models are differential cross sections, right? We need to know what are the final state kinematics, or the kinematics of as many of the final state particles as possible, right? So now now we're going from a total cross section to a differential cross section. So there are a couple new terms. So first of all, there's d sigma dx, right? That is your differential cross section. And then, what we want is we want this in truth space, right? Because our models exist in truth space. And so that's represented by an index I. So this is the ith bin in truth space. And then the index J represents our reconstructed space, right? So I talked about how our detectors have finite resolution and that they're smearing. And so this U in the equation here is a smearing matrix. And we have to undo that smearing, right, to get back to the truth. And then, so in the reconstructed space, we're in the jth bin, and in each one of those bins, we select a number of events, right? We count them, but then we have a purity correction, and the purity correction only exists in reconstructed space, right? So the purity has an index of J. And then the efficiency, however, is always in truth space. And so that has an index of I, right? So the numerator is mostly all in reconstructed space, but then we have to unsmear it, and we have to unfold it to go back into truth space. When we've done that, then we can apply our efficiency correction as a function of the true variable. And then there's the width, the bin width, which is this delta xi. Okay, so this is a differential cross section. So what is X? What are the variables that we want to report? So first of all, we have to define our signal. So theorists and model builders typically think in terms of like a quasi-elastic interaction or a resonant interaction or a 2p2h interaction, right? Because they're developing the models that address those types of interactions. But there are final state interactions, right? In our real world, right? When we're making a measurement, there are final state interactions, for example, pion absorption or charge exchange. And our own detector limitations, right? Our resolution. And so it's impossible for us to measure these processes directly. We can't measure all of them, we can be fooled, right? So for example, consider a case where we see only one muon and one proton in the final state. Well, this could be for a multitude of reasons, right? It could be what we might think is just, okay, it's a quasi-elastic interaction, right? That is the final state, right? A muon and a proton in the final state. But it could also be a resonant interaction where now the pion is absorbed in the nucleus. Or it could be a 2p2h interaction where one proton has energy below our detection threshold, which let's say is, I don't know, 100 MeV. I'm just throwing that number out there. Instead, we can't claim that whatever we're measuring is a quasi-elastic interaction. I suppose we could make corrections, right? We could subtract out those things that we think are not the quasi-elastic interaction. But now you're relying on a model to tell you exactly how much that background is, right? You have no way to really constrain that. And so the best thing to do is to be honest and clear about what we are measuring, which is CC interactions with in this case, a nu mu CC interactions with a single proton above 100 MeV in the final state. Okay, so the types of things that can happen in the final state are shown in this figure here, right? You have your interaction modes, right? Your CCQE, your CCRes, your 2p2h, but then all sorts of things can happen that give you topologies, right? The particles in the actual final state that come out of the nucleus that we can see in our detector, right? So, and we typically break those down as CC0 pi, right? We don't see a pion in the final state, or maybe CC1 pi. These are kind of resonant-like, where we expect to see one pion. And then we could have 0 pi plus NP, right? So maybe more than one proton in the final state, right? And definitely no 0 pions. That would, right? So they're very similar, right, to the QE, the res, and the 2p2h, but they're defined by their topology, right? So this is important. So again, theorists would love to see cross sections reported as functions that they think about, right? They think of their models in terms of neutrino energy or Q squared or W. But these are all cross section model dependent variables, right? So in order to get the energy of a neutrino, we have to use the cross section model itself to make corrections for things that we don't measure well or things that we can't see at all. And then Q squared and W are basically derived from that neutrino energy. And so if you do report things as neutrino, these what I call derived variables, it makes them hard to interpret at face value. All right. So if we make a measurement and we use a particular generator to estimate the neutrino energy and the Q squared. If we want to compare it to another generator, well, it's not really an apples to apples comparison because you've now you've biased yourself to one model, right? And so they're a little hard to interpret, and because there is this model dependence, you now build in potential bias into these derived variables, right? So the cleanest measurements are those that report the final state kinematic particles, for example, those that we can measure directly, right? Things like lepton energy and angle, or or the longitudinal transverse momenta, and similarly for the hadrons, right? The hadron energy and angle, right? So if we can measure those final state kinematics, those are the cleanest measurements that we can give to the community. Okay, so now let's say we've decided what we want to measure. So now we have to develop and optimize our event selection. So our event selection is all about maximizing both our efficiency and our purity, right? So, excuse me, we want these to be as close to one as possible, right? You want to be very efficient and you want to be as pure as possible, right? Now it's best to use observables that when we're trying to identify events that we think are signal, it's best to use observables that characterize particles in the final state. For example, particle ID based on perhaps DDX or scattering or time of flight or Cherenkov flight, etc. So for example, in NOVA, we use the DEDX information, the energy loss information, and the scattering information of the reconstructed charged particle trajectories to isolate muons from other particles, right? So we have 4 different measurements of or ways of looking at the DEDX and scattering, and we put them all together into a multivariate muon ID, which is shown on the bottom right here. So this is as a function of our muon ID cut value. So the muon ID goes from -1 to 1. As we move along in the value that we're cutting on, we can look at our selection efficiency and purity, right? So our selection efficiency, it goes like this, right? So it goes becomes very high here, and then but the purity drops down as you move up in your cut. So you want to develop a figure of merit that is used to maximize the sensitivity of your measurement. This is true for really any analysis, right? When you're trying to make any sort of selection, you want to do it in a way that maximizes your sensitivity. So if you look at the cross-section formula, really what you want to do is to maximize your sensitivity, what that means is you want to minimize your fractional uncertainty on the cross-section. And so if you work out the math, you end up with looking at the fractional uncertainty on the purity, the fractional uncertainty on the efficiency, and then you want to get as many interactions selected as possible as well. Okay, so it's a balance here, and as it turns out, that for this analysis, it's very flat in here. Our figure of merit, right? It drops down and then it goes up, right? But the minimum cross section, the minimum uncertainty in the cross section is shown here at this value. Okay, so this is generally true that you want to come up with a figure of merit that maximizes your sensitivity. And in the case for cross sections, this is one way to do it. Okay, so once you've decided what you want to cut on and that kind of thing, you want to besides maximizing your figure of merit, you want to also check that the selection efficiency doesn't drop too strongly for the things that you are measuring. So for example, if muons cannot be identified below a certain energy, let's say, I don't know, 400 MeV, then consider changing the phase space of your signal to include only muons above this signal, above this threshold. What that means is, instead of saying I'm measuring all muons from 0 to whatever, 5 or infinity, I'm only going to measure muons. My signal is muons above 400 MeV, right? Because if you can't say anything below 400 MeV and you're claiming that you're measuring it, then really what that means is you have no data, because you can't select it. You have no data to make a measurement below 400 MeV, and you're basically relying on your simulation to give you the answer, which is not providing any new information to anyone, right? And it kind of muddies the water. So you want to have a clear definition of your signal and you want to take these types of thresholds into account. Now, you also want to be sure to check that the selection efficiency doesn't depend too strongly on things that you are not measuring, but also have large uncertainties. So, for example, maybe the muon selection efficiency as a function of hadronic energy in the final state, right? You want to look at that. Is that flat? Is it changing rapidly? Or maybe the pion selection efficiency as a function of lepton momentum transfer, Q squared, right? So yes, Q squared is a model dependent derived variable, but it's still a useful thing to look at. And maybe there's something there that could raise some concerns. Now, whenever possible, you want to compare your efficiency with real data. But not the data, obviously, that you are using to make your measurement, right? So you want to have an independent data set where you can kind of check your efficiency. So, for example, for muons, maybe check your muon selection using cosmic rays, right? That's a separate source of cosmic rays. Or maybe check your electromagnetic shower selection using Bremsstrahlung from showers of cosmic rays inside of your detector, right? So those are just two examples. I'd love to hear from you to hear any ideas you have of other sources of data in neutrino detectors that we can use to check our efficiency. Let's see. Oh, okay. I had these swapped. This should have come first. So when I was talking about having an efficiency drop very rapidly, right? You don't want to sit on a rapidly falling curve for your efficiency. That can really blow up your uncertainty. And so you want to stay away from regions where things are changing very rapidly in your efficiency. So in this case, you set a threshold for, kind of where you start to level out. So maybe you set it at 250 or 300 MeV, somewhere around there. But it's kind of really up to, up to your discretion. Okay. Now, so that's for your signal, right? That's for your efficiency. Now getting to the purity term. So the purity is all about backgrounds. So again, remember that simulations are always wrong. And in our case of neutrino interactions, the uncertainties in our backgrounds can be quite large, right? So we simulate the backgrounds, but the uncertainties are quite large. When the backgrounds are significant, and then you have a significant uncertainty, well, that can result in a significant uncertainty in the cross-section itself. But when the backgrounds are significant, then a general approach adopted by most experiments is to use data sidebands, right? So these are data, these are events that are not selected. These are things that fail your selection. And you use these sidebands to validate the modeling of or even constrain the backgrounds. So, for example, in the plot shown here, this is an invariant mass, a reconstructed mass for pi 0, and so the events were selected in this range here, which means that you can look out here and in here. You can look at the events there in data because those are outside of your signal region. And do some comparisons of your backgrounds. Now, ideally, the events in the sideband have similar or overlapping kinematics as the background in the signal selection region, right? So hopefully these events are somewhat very similar kinematically to the background events in your signal region. But honestly, this can be tricky, right? Because background events that look like your signal were probably already selected, right? They're probably already in here. But nevertheless, it's worth looking, and sometimes there's enough coverage that you can get a good constraint on your backgrounds. And so we can actually use the sidebands to not only validate and make sure that things look reasonable, but also to use them to actually reduce the uncertainty associated with modeling the uncertainties, right? So if we expect the backgrounds to have something like at least a priori something like a 20% uncertainty, and then we go and we look at those types of events in our data, but maybe the data in Monte Carlo agreement is much better, And we can use that as a constraint to reduce the uncertainty on the backgrounds of the signal region. So some examples are using nu mu CC pi zero interactions, when in fact you're trying to measure the neutral current pi zero interactions, or maybe the nu e charge current interactions, which give you an electromagnetic shower, and the pi zero, because it decays into two gammas, also creates showers, right? So if you're trying to understand how your selection performs on identifying electromagnetic showers, then there are sidebands that you can use that might give you some insight or some ability to control the level of uncertainty. And then you could use, for example, neutral current interactions to constrain the charge current interactions. Okay, I'm running out of time, so I'm gonna go a little bit faster. So again, here's another question for you all. What are some other examples, other sidebands that we might use for a given analysis? So dream up an analysis and then think about what kind of sidebands we could use. Okay, so analysis variables and binning, as I mentioned earlier, measurements involving direct observables, for example, measured kinematics of final state particles, are the least susceptible to the impact of model bias, right? So again, direct observables, things that we can measure directly, those are the best things to do. But that doesn't mean that we should never look at derived variables. Studying how the cross-section behaves as a function of E nu or Q squared or W, or anything else that relies on some reasonable model can still be qualitatively informative. So maybe not quantitatively, but qualitatively, there should be some features that we expect to happen. For example, at low Q squared, maybe there's a suppression or something else. Do we see that suppression? Maybe we won't get it exact, but do we see it at all, right? And as long as your model is somewhat reasonable, you'll be able to get something qualitatively useful out of that. Now, we also need to take care when deciding how to bin or discretize our data. The bin width should, first of all, never be smaller than our detector resolution. When you do that, you get into very unfortunate circumstances when trying to interpret the results. But also, you want to consider bin-to-bin migration due to systematic uncertainties. Events in a distribution with a rapidly changing slope will migrate asymmetrically across the bins and can result in magnifying the effect. So this is an example where we have a kinematic distribution of muons. This is a reconstructed kinetic energy for muons. And if I were to simply shift the energy by 1%, meaning move this left and right, then this band here represents the size, the relative size, the fraction of events that migrate in and out of the bin as a result. And so this can be a rather big effect. And so, you don't want to make a measurement where this suddenly blows up and becomes, a 200% effect, and then your measurement is maybe not as useful. So in this case, the question is, will smaller or wider bins avoid this issue? And then finally, I want to talk a little bit unfolding. Is this a necessary evil? So our detectors have finite resolution. Furthermore, we have to reconstruct the events on our detectors. We heard from Adam yesterday, and our algorithms can systematically get things wrong. Now, we wish to report measurements that are useful to the community. Therefore, we need to convert our reconstructed observable to a true observable. We rely on simulations to get our smearing right. So we construct a smearing matrix using our simulation because, honestly, it can be a very complicated process, or it's a series of processes that smear things out. And often, this is not really Gaussian in nature. It can have long tails. There can be weird stuff happening. We can construct the smearing matrix by recording the reconstructed variable as a function of its true value. We do that for many millions of events, for example, high statistics, and you can build a matrix, something that's like this. And then we have to undo the smearing, right? Which is an inverse problem, and it's an ill-posed problem, right? So I like to think of this as starting with a blurry image. So here's like a really nice clean image, and then you apply Gaussian blurring. Our problem is the opposite. We're starting with a blurred image, and we're trying to get back to this, right? And so the blurred image has less information, right? There's stuff that's happened to it. And to recover, to go back from this to this, you have to make certain assumptions, right? You can do this, but you have to make certain assumptions. And in our case, those assumptions are our model, our cross-section model. But even if the model were perfect, we can't simply invert the matrix, right? This can give disastrous results. So the classic example shown here is where you have a true distribution of some observable y, and then you go out and you measure it, and the dashed line is your measurement, your observed distribution, and the expected distribution would look something like the solid line, right? But if you were to simply take your matrix, your smearing matrix, and just do a simple inversion, then the whole thing blows up. This would be applying that inverted matrix to the dash line. You end up with this crazy distribution there that looks nothing like this, right? And so this is a result of bin-to-bin correlations and sometimes limited statistics. They can introduce wild oscillatory behavior in the unfolded spectrum that we really want to avoid. And so to avoid that, one has to apply some kind of dampening to reduce these effects. And there are different algorithms that are in use for unfolding, but most of the algorithms have some sort of dampening parameter in them. And the level of dampening is often left to the discretion of the analyzer. There are some general best practices, but there's really no hard and fast rule on what exactly and how to do this. So to unfold or to not unfold, that is the question, right? So we have our result. If we unfold, then we provide the community with a cross-section as a function of true variables. I would say most theorists really like this. There are some experimentalists who are disgusted by it and get very angry. Now, an alternative approach is that we simply measure our event rate, dn dxj, remember J is in reconstructed space, and provide the community the rest of the information they need to compare predictions, right? So we give them the smearing matrix, we give them our purity and our efficiency and all of the other information, and we just let them use that information to compare their models. I am skeptical that this is making things easier or better, and I think that most theorists are not really all that excited about having to do all of this extra work. Now, no matter what you do, both involve unavoidable model dependencies, right? This matrix you're building a model into it, right? And so no matter what, you're building something in there. So again, the challenge is to keep this to a minimum, right? You want to make the model dependence as weak as possible. Now, in both cases, no matter what we do, it's important to make all of the pieces that go into a measurement available as they may be needed for future analysis. And so that's my last slide. And so tomorrow, now that I've explained kind of how we go about making neutrino cross-section measurements, tomorrow I will cover what we know, what we've measured, and what we know we don't know about neutrino nucleus scattering at the GeV scale. And again, I encourage everyone to please send me questions via email or Slack. Thank you.
Thank you, John. So we can have a few questions. Okay. Hello, can you hear me?
Yep.
So my question is regarding the purity selection you were talking about. So is that the purity of selecting a particular interaction process, like whether you are selecting the QE process correctly or not, or is it a general like selection purity of a neutrino interaction?
Yeah, so well, okay, so depending on what you're measuring, the purity is in this case it's reflective of the event itself, right? So if you're looking for, let's say, a charge current, a nu mu charge current interaction, right? When you select an event, let me go back to the definition of purity here. When you select an event, what fraction of them are your actual true signal, right? So you think of it that way, right? Now there is an impurity in that maybe you selected the right event, but you got the wrong particle, right? So I gave an example back here where you've picked the wrong particle as your muon, right? You've picked the right event, right? You think this is the muon, so therefore you think it's a nu mu CC interaction. So you got the event, but you got the wrong piece here, the wrong particle is the muon. And so in that sense, there is an impurity here, but that impurity is basically accounted for in this mixing matrix or this smearing matrix here. Okay, that's where part of the model dependence. You know, how often does that happen? Well, it's accounted for in here.
So this will affect, as I was confused, like this will affect like what process we are actually looking through our final state particles. But like there are the three event generators you showed, the results for three event generators for the cross section, they differ a lot. So I think even if you misidentify the particle, at least you are sure that the interaction took place. So the total cross section is still varying. So like, should it not match a little bit?
So these predictions here are for nu mu CC interactions themselves, right? So it's a pure prediction, right? There's no purity effect here at all, right? Because we're not dealing with real data, right? We're not having to we in simulation, right? We're God, right? We know the truth, right? We know everything, right? In principle. And so there's no doubt, right? There's no way to get it wrong, right? And so these are absolutely, you know, 100% pure. Now, when you look at data, we're not God, right? So we don't know if it's real or not. But we have to estimate, you know, how often do we get it wrong, right? And that's where the purity correction comes in.
Thank you.
Mm-hmm.